Okay, this is the last topic for rigid body equilibrium. It's 3D rigid body equilibrium. If you can find this book, it's a fun book to read. It's called Flatland, and it's about all these geometric shapes that live in 2 dimensions. And they have a talk about what life is like on a plane. It's interesting. For example, an arrow, when you look at it straight on, it disappears, and things like that. Anyway, this is 2D. Flatland is 2D, but what we're doing now will be 3D, not Flatland. The main concept of equilibrium doesn't change. It's still the forces add up to zero and the moments add up to zero. It's just now that these vectors are 3-dimensional instead of 2-dimensional. What that means, in 2D, we had 2 forces, and there was only one moment, spinning counterclockwise or clockwise, so we had only 3 unknowns. In the full-blown 3D, we have 3 forces, and we have 3 moments. And we talked about the moment vector, how you point your thumb along the moment vector and it spins about there. But that has 3 components. So in the end, if you have a true 3D problem, you end up with 6 equations, which means for the problem to be solvable, you'll have 6 unknowns. Just like in 2D equilibrium, 2D rigid body equilibrium, in 3D rigid body equilibrium, you need to know about supports. And there are many, many options. So before we go through the options, let's just talk about this. You could have, at a support, 3 forces, and you could also have 3 moments, depending on the type of support. So a truly, completely fixed support will have 6 reactions, 3 forces and 3 moments. Well, you can have all sorts of combinations and permutations of these 6 things, and therefore you have many, many options. And in fact, if you were good at combinatorics or statistics, you could tell me how many options you could make out of 6 things. Table 5-2 in your book lists many, many options. I've just listed a few here. You can go through them. Actually, let's just walk through these. You could have a cable as a support, and you would have 1 reaction there. A smooth surface support, you would have perpendicular to the surface. A force like that, or a roller, will be perpendicular. That means 1 unknown, so 1 reaction. Here you have a ball and socket joint. I have like a pen that can rotate, that my pen goes in, something like that. This type of reaction here has 3 forces but no moments, so it has 3 reactions. And here you can see that this has 2 forces and 2 moments, but it can spin about this axis. It can spin like that, and it can also slide this way. Okay, and this is called a single journal bearing. So you MEs, you'll have to understand how these things work. The main thing is that this thing has 4 reactions. Okay, and this is a single journal bearing with a square shaft, meaning it cannot spin. So there is a reaction that way because it's square, but it can slide in and out. So basically it has all 6 reactions except for this force there, which can slide back and forth. So this one has 5 reactions. Okay, this is a thrust bearing, and what a thrust bearing does is this thing is free to rotate, but it cannot slide in and out. And here you have, again, 5 reactions. And this is a single smooth pin. You cannot twist it out of the plane, and you cannot move it in any direction force-wise, so this also has 5 reactions. Okay, and then here is a hinge. This adds up to 5 reactions, and this is completely fixed with all 6 reactions. these ones that have less than 6, they basically you release one of the motions. So a hinge here, it can rotate, and the other ones have one direction or angle that it can rotate, and all the others are fixed. Now, on a computer, how we would do this is you would have a box like this, a menu, FX, FY, FZ, MX, MY, MZ. And when you go on a computer, you just check all the things that cannot move, and that would tell you those things all have reactions. So in 3D, I'm used to this. It's just give a list of 6 and you just start marking off the ones that can't move, and that means you'll have a reaction there. So speaking of computers, I want to take an aside and just say a few words. I was in New Zealand once, and a colleague asked me, "Do you have beers in Wyoming?" I go, "Do we have beers in Wyoming?" I said, "Yeah, we have beers in Wyoming. We even have beers on campus." This was back when we used to have the beer garden in the Union. And he was just shocked. And he goes, "Wow." Then I found out he was saying bears. They pronounce bears, beers. And so he thought, wow, life in Wyoming is really hard. You have beers on campus. But it made me laugh, but then it made me think, sometimes life is hard. We don't have bears on campus, but, I've seen bears up at Happy Jack. And I think of 3D statics like that. Sometimes life is hard. You have these complicated problems. That's why we have computers. And to be honest, I often will do 3D problems. When it gets to that point, I'll model it on a computer. I will not solve it by hand. Although there has been once in my life where I had to solve some kind of problem on a big PhD exam. It was 3D, and being able to solve it helped me out quite a bit. But anyway, 3D problems are hard. We do have computers to help solve them. You will do a few in this class.